Alright, the next one we want to do is problem 51 from chapter 9. In this figure, a 3.5, so the mass of the bullet is 3.5 grams. A 3.5 gram bullet is fired horizontally at 2 blocks at rest on a frictionless table. The bullet passes through block 1, the mass is given 1.2 kilograms, and embeds itself in block 2, mass 1.8 kilograms. The blocks end out with speed, so the first block is moving at 0.63 and the second block is moving at 1.4. Neglecting the material removed from block 1 by the bullet, find the speed of the bullet as it leaves and enters the block 1. So in other words, you fire a bullet. You know the mass, but you don't know what is the initial velocity, and you don't know how fast it moves after you strike the first block. So what we know is that after the bullet, passing through block 1 after collision. So this is a typical collision problem. So it's a collision between the bullet and the blocks. So the bullet, once it passes through the first block, the block acquires a velocity. It's moving in the same direction, and simultaneously the bullet continues its track and then strike block 2. And then once it strikes block 2, it's actually embedded in block 2, and the whole thing is moving at velocity that's 1.4 meters per second. So we asked to find what is the velocity for of the bullet before it enter the block 1 and after it leaves the block 1. So we call that V naught and V. So your task is to find what is the initial velocity, what is the final velocity when it leaves block 1. Okay. So how do we approach this problem? We can see that this is basically an inelastic collision problem, so you don't assume that energy is conserved. What we do know is that when you have an inelastic collision, momentum has to be conserved. Okay? So based on this diagram, this bullet has initial velocity, and so it has a needed momentum. And the needed momentum would just the initial velocity of the bullet times the mass of the bullet. And so you can see that. So the needed momentum and the final momentum has to be that. So this is in a linear situation, and this is when when it passed through block 1 and embedded itself into block 2. So you can actually skip. You can just take this as your initial and take this as your final state. So in that case, initially. So your PR is equal to PF, and because we're dealing one-dimensional, so you can drop the vector sign. So initially, we have mass of the bullet times the initial velocity of the bullet. That's the only term that contributes to linear momentum, because the 2 blocks initially are motionless. And then let's see. We should actually look at taking, because if you take this, let's say, what do we do? MB plus M2. So if we take this has a linear momentum, and this one has MB, this one has MB times the velocity. So let's say if we take okay, so because if you set this equal to that, you're not going to. If you set this equal to that, that can do, and also this will be equal to that as well. So you can actually set it that, once this one bullet strike the first block, then it emerge with the velocity v. So you can have the linear momentum, that's mass of the bullet, and then times the velocity v. Okay, and that's the linear momentum during at the striking point, and then that has to be equal to. That has to be equal to when this thing is moving rightward. So you have MB and then plus the mass 2, and then the whole thing has a velocity that's 1.4. So in that case, you can calculate the velocity. You can calculate the velocity when when you emerge from block 1. So what you have here is that 3.5 times 10 to the negative 3, and then times V, which is unknown, and that's equal to 3.5 times 10 to the negative 3, and then plus M2, and your M2 is 1.8 kilogram, and then times V2. So your V2 is 1.4. So in that case, you can calculate what is the velocity when it pass the first block. So once you do this, you will get your velocity you'll get your velocity that's equal to 721.4 meters per second. Okay, so this is when we have a bullet that's passing through the first block, and then after the collision, it has the velocity with this magnitude, and that velocity is continuing to pass through. So we can actually break it like, so the diagram will be like this. So you have your M2. So this is your M2, and then you have the bullet that's moving with the velocity v, and then striking the M2, and then embedded in here, and then the whole thing is moving with the v2 velocity. So that's basically the diagram and the approach that we take, just by taking it this. So you can calculate your velocity after before you enter block 2. That will be the velocity of the bullet. And then once you have that, then it becomes easy to calculate initial velocity of the bullet, because again, we're going to use the conservation linear momentum. So you have your mass of the bullet, and then times initial velocity of the bullet. That has to be equal to so this, now we're focusing on this part. So you have the bullet initially carry linear momentum, and it's going to pass transfer its linear momentum to the bullet and also to the block 1. So before collision, you have mb times v naught. After collision, you have mb and then times v, because the bullet carries the velocity, and then plus, in addition to that, this block after collision is also moving at the velocity as well. So you have your m1 and then times v1. Okay, so that's basically what we do. So you have 3.5 times 10 to the negative 3 v naught, that's equal to 3.5 times negative 3, and then times the velocity which we just found, and then plus m1. m1 is 1.2, and the velocity is 0.63. So you can see that we can calculate our v naught. So your v naught here is equal to 937.4 meters per second. So this is a very typical problem that deal with that you have to apply use the concept of conservation linear momentum. What is before and what is after. As you can see, you can set up equation. You will actually set up equation just based on this diagram. Most of the time, you have a linear momentum, and it has to be equal to after you strike. So by logical sense, you will actually set up equation by beginning from this step. But because when you look at this, we have all the information, but we don't have the initial velocity. We don't have the final velocity of the bullet. So you can't directly set this equation and trying to find the answers. You have to actually utilize the other part of the information, and that information will be that when the bullet emerge with this velocity, then you treat that as your initial velocity of the bullet, and then look at the interactions of the bullet with the collision between the bullet and the second block. So this bullet will carry a linear momentum, and that is equal to after so during this complete inelastic collision, then the mass, and then times the velocity. Okay, so we kind of we have to do it in a reverse order. This is basically by intuition. You would set up an equation like this, but unfortunately, because there are two unknowns, you can't just use this equation to solve for the two unknowns. So you have to utilize this part. So treat this as initial and the final, and then after you have that, then you can treat this as your initial and this is your final, and then calculate the velocities. Okay, so that's that. The next one we want to do is problem 52. All right, so this is the diagram. Problem 52. A 10 gram bullet moving directly upward at 1,000 centimeters per second strikes and passes through the central mass of 5 kilogram block initially at rest. The bullet emerges from the block moving directly upward at 400 meters per second. To what maximum height does the block then rise above its initial position? Okay, so you have a block initially at rest, so that it does not have any linear momentum. But you do have a bullet that is moving at this velocity, so we know that there is a linear momentum right there. And then it strikes through this block. So what's happening is that when it's moving past the block, it's going to transfer its energy and momentum to the block in such a way that the block actually acquires a velocity, and it can actually move upward, and then simultaneously this bullet emerges, passing through this block, and is moving at the velocity that's 400 meters per second, and the whole thing, the block will reach the maximum height. So during the maximum, when it reaches the maximum height, it has no velocity. So all its energy is actually being converted to the gravitational potential energy. So you can see that this is a problem that involves the concept of energy and linear momentum. Which one is conserved? You'll find that during different process, there are things different quantity is conserved. So let's see, during this collision problem, you have the bullet that's moving at a velocity and it's moving upwards. Okay, so when it's moving upward, then we know that it is moving. So, and it's going to, the linear momentum has to be equal to the final linear momentum. So during the so there's intermediate steps. So when the bullet transfer its linear momentum to the block and also retains some linear momentum to the bullet itself. So let me just. So in other words, intermediate step will be when the block acquires a velocity. So let's say we use that so it's moving at the velocity, we use that v, and then the bullet of course is moving at that velocity. Okay, so and then this block will continue to move until you reach the maximum height. And you'll also find what is the maximum height. So let me just draw a level case. Okay. All right. So based on this diagram and that diagram, we know that this is the linear momentum, and then there is a final linear momentum, and they have to be equal to each other. So that's Vi is equal to Vf. Okay. What is our Vi? Vi, which is the mass of the bullet times the initial velocity of the bullet. So that's known, and Vf, Pf, what is the final linear momentum? This block is moving at the velocity, okay? So capital N times the velocity. The mass of the block is given. The velocity we don't know, okay? And then there's a bullet that's passing through this block. It's moving at that velocity. So final velocity. So you have your Mb and then times Vf. So this has to be, linear momentum has to be conserved. So you have the linear momentum, you have the final linear momentum. So you might ask, why are we finding this velocity? So we're going to explain why we're going to find this velocity, because because this velocity basically gives the block the kinetic energy, and that kinetic energy is going to be converted to the gravitational potential energy, so that you can find your heights here. Okay. So now that's plug in the numbers that we have, and then times 1,000. That is equal to 5v, and then plus this, and then times this. So you can see that how fast is the block moving after collision? It will move at this velocity. Okay? When the block is moving at that velocity, we know that it has kinetic energy. And that kinetic energy will basically, so you can treat this as the initial velocity of the block, and then once it reaches the maximum height, when the final velocity of the block will become 0. So in that case, you will have all the kinetic energy of the block. That has to be equal to all the kinetic, all the gravitational potential energy. Okay, so the mass of the block basically just cancels. So you have 1/2 n times the velocity, which is 1.2 squared, and that's equal to 9.8 times the height. So what is the maximum height the block can attain? That will be 0.073 meters. Okay, so you can see that this problem utilized the conservation of linear momentum. It also utilized the concept of conservation of energy. You can't just use the conservation energy during the first part because because this is an inelastic collision. Now once they collide with each other, this block acquires velocity, and that velocity comes with the kinetic energy, and that kinetic energy converted to gravitational potential energy. This part energy is conserved, okay, but during this part energy is not conserved because it's an inelastic collision. Okay. All right. So the next one we want to do is problem 58. Okay, so let me draw the diagram first. This. Okay. And collision. All right, so problem 58. In this diagram, block 2 that has a mass of 1 kilogram is at rest on the friction surface and touching the end of an unstretched spring or spring constant 200 Newton per meters. The other end of the spring is fixed to a wall. Block 1, which has a mass of 2 kilograms, traveling at a speed that is 4 meters per second, and collide with block 2, and then the two blocks stick together, and then when the block momentarily stops, by what distance is the spring compressed? Okay, so this process involves a lot of concepts. All right, so what we have here is that this is initially at rest, and this is moving rightward with the velocity, so we know that it has a linear momentum. And when they collide, you can say they stick together. What does that mean? It is a completely inelastic collision. So energy is not conserved during this process. When energy is not conserved during this process, you cannot use the conservation of energy to find out the velocity. You have to use the linear momentum, the conservation linear momentum. And so they stick together. Now, when they stick together, they move at the same velocity, and then the whole thing is going to continue to move, and you can see that all this kinetic energy is actually converted to the spring potential energy because during this part energy is conserved. There's no friction, so energy is conserved during this part. During this part, from this part to that part, energy is not conserved, but linear momentum is conserved. So that's based on this, we can actually start finding out what is the velocity after collision when they stick together. So initially, the linear momentum is m1v0. Okay, this is the only one that has linear momentum. After collision, they stick together. So you have your m1 plus m2, and then times the same velocity v, so that we can just plug in the numbers. So you have 2 times 4, and that's equal to 2 plus 1 and times v. So your v should have a value that's 2.67 meters per second. Okay, so you have your velocity, and the whole thing is moving, which means that it carries kinetic energy. And the whole thing will momentarily stop. So which means that since energy is conserved, we need to figure out what kind of energy are present. During this move, the only energy that it has is just 1/2 mv squared. Okay, and the m here would just be, I should say that it should be m1 combined mass, m1 plus n2, and then v squared. This is the only energy that's present, that's kinetic energy. And after collision, after they, and then after it momentarily stop, which means that the velocity here is 0. So it loses all its kinetic energy and convert it to the spring potential energy. So that's 1/2 spring constant and then times the displacement. So you also find what is the maximum distance that the spring will be compressed. So we have all the information in front of us. You have 1/2 and you have 2 plus 1 and then you have the V square, and that has to be equal to 1/2 your K is given, and then your D. So you have your D value. After you plug in the numbers, that should be 0.325 meters. Okay, so that's basically a very cool problem that involves the concept of conservation energy and also conservation linear momentum. Alrighty, I'll stop here.